Hello everyone, and welcome to the third video in the Class 8 series of lecture videos. Today we're going to go through the exothermic elementary step for a radical chlorination of methane. In review, Hammond's postulate describes elementary steps in a reaction mechanism. In the elementary step that follows that first elementary step that we looked at in the second video for the Class 8 series of videos, the methyl radical becomes chlorinated. So the methyl radical bumps in to diatomic chlorine. So you might ask, why is it bumping into diatomic chlorine? Why isn't it bumping into a chlorine radical? Well, remember, for initiation, only a small number or small concentration of diatomic chlorine was homolyzed to create chlorine radicals. There's much more diatomic chlorine gas in our reaction system than there is chlorine radicals floating around. So it's much more statistically likely that our methyl radical will bump into a diatomic chlorine molecule than bumping into a chlorine radical. Everything, of course, is possible, but statistics sometimes controls the overall outcome of a reaction, or say gambling in Las Vegas. Anyways, when our methyl radical bumps into diatomic chlorine, what happens? Well, it abstracts a chlorine. It breaks the chlorine bond. We form the methyl carbon chlorine bond, and we regenerate a chlorine radical. And so the change in enthalpy for this elementary step is minus 27 kcals per mole. And this has to do with the fact that our chlorine-chlorine bond is worth 58 kcals per mole, and our carbon-chlorine bond is only worth 85 kcals per mole. And so the difference, of course, is minus 27 kcals per mole. I need to stress that the relative concentrations, that is, of the methyl radical or the chlorine radical, for instance, doesn't need to be high for the reaction to proceed. Also notice that there is no change in enthalpy for the initiation step, since it only needs to happen infrequently to kick off the reaction. It's really taken into account that initiation step, the breaking of the chlorine-chlorine bond. It's really taken into account in this second elementary step, this propagation step. So, in terms of an energy versus reaction coordinate diagram, now I've put together our first elementary step, where we started off with the chlorine radical and methane, and we generated a methyl radical and HCl. Now this was an endothermic reaction. We saw that the activation energy was 4 kcals per mole in terms of height from our starting reactants, and our the change in enthalpy for that first step was positive 2 kcals per mole. Now we're looking at the second elementary step. We're looking at the methyl radical bumping into diatomic chlorine. And so that's associated with that is a transition state. We'll call it transition state 2. And the products of that reaction are going to be our chloromethane and regenerating a chlorine radical. Now the change in enthalpy is approximately 27 kcals per mole. And this is, again, an example of an exothermic reaction. So according to Hammond's postulate, now the transition state should occur early. It should occur close to the reactants, and the structure should look more like the reactants. So it should look more like a methyl radical and diatomic chlorine. So, in words, for an exothermic reaction, the transition state, double cross 2 in this case, looks more like the starting reactants than the products. It comes early in our energy versus reaction coordinate diagram. Please understand how to apply Hammond's postulate to draw or interpret reaction coordinate diagrams. I don't think I ever ask students to draw or interpret reaction coordinate diagrams in exam settings, but I could always throw a curveball for a given exam. Next, we can consider termination steps. While statistically unlikely, reactions are big places, lots of reactive species bumping around, so they might run into each other. So for example, chlorine radicals could simply recombine to form diatomic chlorine. A methyl radical might bump into a methyl radical, and you might generate, ethane in your radical halogenation of methane. And again, while statistically less likely, you could indeed have a methyl radical combining with a chlorine radical to give you chloromethane. Taken as a whole, initiation, propagation, termination, we've described a radical chain reaction, and in the case that we just discussed above, it's a radical halogenation. So why don't I go ahead and sum up those elementary steps that sum to the overall reaction. Well, so as I said, that initiation step, we don't take into account the enthalpy. Why? Because we don't need to break an entire mole of chlorine, diatomic chlorine, to create 2 moles of chlorine radicals. We only need to create a few of these chlorine radical species, and so that few is insignificant in terms of energy, because once we create that chlorine radical, it's going to bump into methane, create a methyl radical and HCl, and then that methyl radical is going to bump into diatomic chlorine. Because we have mostly diatomic chlorine, the light only broke a few of the molecules into chlorine radicals, and that's how we're going to generate our chloromethane and regenerate a chlorine radical that goes back to propagation step 1. And so we have the enthalpies for those 2 elementary steps. If we add these 2 reactions together, we can cancel the methyl radicals and the chlorine radicals, and we sum to the overall reaction, and we sum to the overall enthalpy of reaction too, of minus 25 kcals per mole. So in the next video, we'll consider reaction kinetics a bit more.